right? We were focusing on BGP attribute. We just started actually, no? We saw different classes of attributes, and then we spoke about some well-known attributes, means well-known mandatory, well-known discretionary attribute. We also spoke about MED, which is optional, non-transitive, and then at last we finished with wait, Cisco proprietary called wait, Cisco only attribute called wait. Now, this is also a page which we might have covered, but I would like to repeat it because it's very important. So from here we are going to continue our BGP class today. We know about this protocol. This is special. That's why we use between the borders. Though it is very special protocol, this cannot do load balancing. When you got multiple paths, from multiple paths, BGP will have a very clear reason, one good reason to say, I'm going to choose this one single path. It will eliminate all other paths and pick one single best path based on the policy, which is through attribute. Policies, how do we apply? Through attributes. Using attribute, the policies are identified by the router. How router knows your policy? Based on the attribute. Based on the attribute configuration, based on the attribute. And it picks one best path. I used to say, no, in the previous class I have told this. In front of you there are two beautiful cars, looks similar, but you still pick one car saying I want only one, maybe based on the engine number. You like that small engine number than the big number on the engine. Though other things are looking similar, you have a reason to say this car I prefer because of this. Likewise, after thorough iteration, BGP can pick one single best path by eliminating all other paths. Again, the main reason why I opened this page for today's class, though we have covered it earlier, the main reason for covering this once again is to talk something more on this point. This is not only related to BGP, this is also very important routing fundamental. You see, BGP has picked one best path, but that is not going to guarantee that that path is going to be utilized by the routing table. See, the best path for, according to BGP, there is a path selected and it is submitted to the routing table manager process. But path selection, BGP is not the only one which does the path selection. The routing table manager also has got his own role in deciding whether to keep it or not. So what it does, it evaluates. Who evaluates? The routing table manager evaluates. See, this is not only for BGP, this is for every routing protocol. If OSPF gives a route, routing table will say, wait a minute, let me check whether you are good or EIGRP is good. Sometime, we'll be running multiple routing protocols on the same router. And all the protocols may give a path for destination. So now routing table manager need to evaluate against the method of routing protocol for reaching the network. What I mean is the administrative distance. So that's the role of the routing protocol manager, routing table manager. So when a route is given to the routing table manager will not care about it whether it is a very important protocol or less important protocol. It only looks into the administrative distance of that protocol which provides the best route. For the same destination, EIGRP gives, OSPF gives, BGP gives. Which one to choose? Which path to choose? Based on the administrative distance. So routing table will decide to take the best path given by a routing protocol who has got the lowest administrative distance. That's why I said BGP selects the best path, but it is not guaranteed that that will be taken as the best path for the router. So I added few slides to this presentation which was not there earlier. That's why I started with this topic today. This is the new slide and a few more slides. So the path control of packet forwarding on hop by hop basis. So every hop decides. First router decides which route to go. Second router will also decide. Third router will also decide. Maybe first router decides based on BGP's decision. The second router may decide based on the OSPF running on this router. The third router may be based on the EIGRP. So what I'm coming to say is the router has got the final routing table manager process to do. Only now based on the routing table manager process evaluation, whose route to use will be determined. So it's hop by hop basis. This may be a eBGP router. So BGP is preferred there. Administrative distance of eBGP is what? 20. Whereas this becomes an iBGP now because it's inside. When the same BGP route comes in, here it is 20, but when it comes in, it is 200. Administrative distance in router 2 is 200. What is administrative distance of iBGP? 200. eBGP is only 20. So here, even though you have OSPF, eBGP is given importance, 20. Whereas in this router, OSPF is given importance. If OSPF and iBGP brings same destination or path information, whose path is taken by the router? It's the OSPF path. And now this router, you may run OSPF, EIGRP, IGP, IBGP. When all these three provides the same destination route for same destination, administrative distance of EIGRP is only 90, whereas for OSPF is 110. So router 2 is going to decide based on, router 3 is going to be based on EIGRP. So it is hop by hop basis. The control of the packet forwarding. The control is dependent on the administrative distance. The final authoritative person to decide on the path is routing table manager process. To explain that, I have this topology. You see, in this topology we have different protocols. If you take router 4, we have RIP running, we have OSPF running. So multiple routing protocols running there. But whose decision is going to be taken? It depends on the administrative distance, the routing protocol manager, routing table manager. Like this, you see, this is what I was talking about. Different routing protocol provides route to the routing table. RIP is giving route, OSPF is giving route, EIGRP is giving route. But the routing table manager will decide. See, individual routing protocol have no control over what gets installed into the routing table. BGP don't have any control. OSPF, EIGRP, they don't have any control over the routing table. Routing protocol's job is to recommend a route. To whom? The routing table manager, which we saw here, the routing table manager process. So that's what this picture explains us. Routing protocol's job is to recommend some routes as per their knowledge. RIP's knowledge is based on the hop count. It recommends. OSPF knowledge is based on the cost. It recommends. Likewise, EIGRP recommends route to the routing table. But the final authoritative member to decide is the routing table manager. It's the routing table manager who decides whose route to use in the routing table. Whether OSPF given route or EIGRP given route or BGP given, whose route. That depends on the administrative distance. So in this example we got only RIP, OSPF, EIGRP. EIGRP's recommendation is taken by the routing table. EIGRP's route, best route, is given, while RIP route and OSPF also given to the routing table, but routing table installs only EIGRP's route. Right. Again, another story is coming now. Do you think routing table decides the path? No. Routing table has now decided to use what EIGRP recommended. That is true. But there is also switching process who decides the path. Switching process. What are the types of switching process we have? Sorry, those things I'll continue later. You see, again we have switching process. We have Ceph who decides. Most of the switching is based on the Ceph in Cisco. There is also another type of switching called process switching. Process switching. Now what's the difference between the Ceph based switching process and process switching? We know about Ceph. What is Ceph? It's a buffer, it's a memory in layer 2 which stores the path information for destinations. It's a memory in layer 2 which stores the path information for destinations in layer 2 level, so that the packet need not to go through the routing table for every single packet. It need not to go to the routing table to decide on the path. Definitely it reduces the time taken and process utilization while determining the path. Ceph quickens the packet forwarding. It makes the routing faster. Ceph makes the routing faster. But there is a approach to forward when you have two paths. Listen, this is important. I need a space to draw, so I'll use the space. Now, for router 1, it may go via router 2 or router 3 to reach router 4 in order to go to 4.4.4.4. So, in R1's routing table, let's say we have equal cost path. Listen, I'm not talking BGP now. I'm talking path control. We'll get into BGP shortly. Let me finish this basic thing that we all need to know very clearly. Many times, even I was confused for many years with this concept. So I'm making it clear for you. After many years of, I will not say many years of research or many years of study, I got this idea. Once in a while I used to think why it is behaving like this. But after many years I got answer. Now today I am putting it to my delivery. I am applying that in delivery, which I found. Now you see, let's say we got 1.1.1.2. This is how you can test. So I'm drawing the topology here so that you can also check what I'm saying, what you are learning today after the class. Right? Let's say you are running some protocol and that protocol has distributed the route. Now in routing table for reaching 4.4.4.4, you have two paths, one via router 2, another via router 3. You got two paths in the routing table. I told you it doesn't matter who provided this route. It is going to be the routing table engine manager who decides. So we got route in the routing table. We got two routes. But when you try to ping or trace route, you will see packet always going this way or this way, any one of the way, always. Have you noticed it? And I used to like wonder, what is this? Load balancing means equal cost load balancing means I should see both the paths used. I should see both the paths used. But when I trace route, I always see the same path. Then later what I did is I traced the route to this destination with this source address. I noticed the path was going via this way. And now again I traced the path to the destination with this as the source, the second loopback as the source. That time I saw packet going this way. Again, when I use the first one, it is going still via the same router 2. When I use the second one, it goes via router 3. When I use the third one, I saw it is going via router 2. And when I ping with the source of 114, I saw it was going via router 3. Then I discovered Ceph is the reason for that. What Ceph does is, it downloads this route into the routing into the Ceph table. Ceph will also have these two routes. But what it does, it says when this source goes to this destination, then R2 is the gateway. When this source goes to this destination, R3 is the gateway. So Ceph decides that. That's what we saw here. It's switching process that decides the path. Ceph is the switching process that most of the Cisco routers are following. Ceph will not take the traffic from one source to destination and share it. Let's say if I have 500 packets to send, it is not going to send 200 via router 2 or 250 via router 2, another 250 via router 3. No, it's not going to do that. It's not going to share a traffic's load on two different paths. It is going to be based on the source destination. Whenever the source changes, the path will get changed if you have multiple paths. If you have multiple paths, when the source is same, the path is going to be same. When you change the source, the destination is same, okay? The destination is same. But when you change the source, the path also changes. In that way, the load balancing happens. It's not going to take 500 packet and share 50 on this side and 50 on this side. Ceph never does that. But if you cancel Ceph, you will see first packet going this way, second packet going this way, third packet going this way, fourth packet going this way, fifth packet going this way, sixth packet going this way. You will see 250 packets via this way, 250 packets via this way. Where? When you do packet switching, when you don't have Ceph. When we don't have Ceph, the process switching, the switching process is through the routing table. When we don't have Ceph, it's going to be packet switching, meaning every packet will be going through the routing table to decide the path. When you got multiple paths in the routing table, the one with the best, meaning it's not going to be based on the source. The one which is already utilized will not be utilized, the other one will be utilized. So but it's a huge process consuming method. Ceph is good. If you don't have Ceph, you will see that, as I said, traffic will be balanced. Traffic will be balanced on these two paths for the same source and same destination. Whereas in Ceph, balancing is based on different source. Only when you have different source, different path is going to be utilized. Same source, no load sharing. Same source, no load sharing. In Ceph, same source, same path always. Even if you have another 3 paths, it won't be used. Only when the source changes, the other paths will be used. Are you clear with this path control process?
Hello.
Yeah.
So, Aaron, when Ceph will come into the picture?
Ceph will always be.
We have admin distance and each protocol their own load balancing. For example, EIGRP, right? So that can do load balance. So
I told you.
Each router.
Sorry.
For example.
Go ahead.
Okay, each router based on the admin distance, right? By first preference will decide the best path using algorithm. So when that will go, from routing table, using algorithm, it will decide the best path. So when this will come into the picture, based on the source, you said load share, based on the this gateway using source and different source, this gateway. So how that protocol CSF will know when we have all admin distance and all this on the router.
Yes. So you remember, I also told there is no connection between the routing protocol and the path selection decided. There is no connection. Why? It is the routing table manager who decides. How he decides, how it decides based on the administrative distance. So, RIP is giving the route, OSPF is giving the route, EIGRP is giving the route. Routing table manager says, wait, you are all giving your best routes, I appreciate, but I also have a elimination process. So routing table manager says, whose administrative distance is lower here? Oh, EIGRP, come on EIGRP, I take your route. That's all the role of EIGRP. Finished. There is no more contribution from EIGRP in path selection. EIGRP's route is taken in the routing table. Now the routing table shows the direction, the gateway, and if there is multiple gateway, because EIGRP might have given 2 paths, equal cost path or unequal cost, it has given 2 paths. Now among the 2, which path to take is decided not by the routing table, it is by the switching process. See, there is no connection now. Routing table has done its job wonderfully, has given 2 beautiful routes. Now it is the switching process who is going to decide whether I will use both the path for the same source or different paths for different source. The switching process is what called as one of the switching process is what called as Ceph, which is widely seen on every Cisco device. Ceph is turned on by default. Ceph is on by default. So Ceph works like this. How? It sits in layer 2. Listen, this is important. That's why I say there is no connection between the routing table and the packet which is going to be forwarded by the router when you have Ceph on. Ceph has got the complete routing table in a layer 2 level. So no more routing table, it's a Ceph. And how Ceph works? Ceph will see from where the packet is coming to where the packet is going. When any one of this changes, the path will also change. That's how Ceph works. That's why I said in Ceph you should not expect a traffic being shared across multiple paths. See, our Murali's question is, EIGRP has given you 2 routes. You can't use the 2 route. What is that Ceph? Then why that EIGRP should give the 2 route? That's the question he is asking. Answer to his question is, the 2 route is used, but how it is used is what? Different from how you expect. What you expect is EIGRP has given 2 routes, 5,000 packets are coming, so now both the paths should carry the load, 2,500 on one path, 2,500 packet on another path. That is not the way Ceph will work. Ceph will say, okay, I have 2 paths, fine. When A is sending the packet, I will put him in the first path. When B sends the packet, I will put him in the second path. See, I am also using the both paths. Ceph says, I am using both the paths. Who said I am not using it? I am not using both the paths for the same person, but I am using for different person. If A is coming, I am sending via the left hand side road. When B comes, I send him via the right hand side road. See, I am utilizing both the paths given by EIGRP. That's the method, that's the switching process that Ceph follows. If you cancel Ceph, then you will see routing will be based on the routing table. Why? Ceph is in the layer 2, you have spoiled it, you have cancelled it. Now all the packet has to go through the routing table all the time. And routing table says, okay, take this path, first packet. Second packet, take the next path. Third packet, take the first path. So if you cancel Ceph, the process switching comes. Meaning every packet will be processed by the routing table, which is going to consume a lot of processor. Every packet will be checked against the routing table, and if you have multiple paths, for every single packet, path will be determined. So as we spoke, the first path will go via the first packet will go via the first path, second path will be going via second packet will be going via the second path. But there's going to be a very big process consuming forwarding. If you're okay with that, you can cancel Ceph and you can have your both the paths used for every source. As I said, if you have 5,000 packets to send, 2,500 will be sent via path 1, 2,500 will be sent via path 2 for the same source. But after long research, Cisco has found that it's not good to do process switching, going to the routing table for everything. That's why they designed Ceph in a layer 2 level. Ceph is good, so don't cancel it. Ceph is enabled by default. So in short, what I want to tell Murli is, EIGRP given paths are utilized by Ceph, but for the same source, it won't use multiple paths. When the source changes, path changes. You got multiple paths for the destination, and you also have multiple source to that destination. When source changes, the path changes. When the source is same, the path will not be different. It will be same for all the packet, means for the complete flow of traffic. Yes, Murli.
So around same source, you want to use multiple paths, right?
Correct. In Ceph.
So what if the traffic comes second time?
Same path.
Same path, okay. And why it is if the source change, why it is going on the second gateway?
Because you got gateways available, you need to utilize, no? That was your early question. EIGRP, after long struggle, it has given you two best paths. Why are you using the same path? Why are you wasting the other path? That's what your question, right?
And what if we have the C1 113?
That will go to the first path.
Okay.
Kind of round robin.
Okay, got it.
Yeah.
Okay, got it.
So these are all automatic. That's why we have not focused on these things for many years. Some of you are 10 years experience, 12 years experience, but we have not thought about these things because these things are happening automatically. But only when you know these things, when you become an architect, when you become a troubleshooter, some big guy in networking, you will know why the packets are going like this. When you debug, you will not get an answer if you don't know this fundamental. I was stuck for many days, many years, and I was not really focusing much on that, but I know there is something different. EIGRP should load balance, but when I trace the route, when I debug, I'm not seeing load balancing happening, and I was like, why then EIGRP gave multiple paths? Same question what Murli asked, I was asking myself for many years. And later, when I was studying about Ceph in depth, I found it's going to be source-based load balancing. Aha! So, whatever the routing protocol gives, routing table is not going to care about whatever, who are you, those things. It only cares about the administrative distance. And whatever the routing table gives, Ceph doesn't care about it. Ceph has got its own method in deciding the path. So path control, in short, what I want to say is, it is partially dependent on routing protocol, partially dependent on routing protocol manager, and partially depends on the switching process. That is the meaning of this two paragraph. So it was clear only when we read this two paragraph. It's the same meaning we got, but I don't know how many of you got this depth knowledge of what we covered now. We have studied this page in the previous class. The best path is submitted to the routing table manager and manager process and evaluated against the method of other routing protocol to reach the network, and bracket this administrative distance. So the route from the source with the lowest administrative distance will be installed into the routing table. So if it is OSPF and EIGRP is the source. EIGRP is the source whose administrative distance is lower. Now once the administrative distance based evaluation is done, routing table got the EIGRP route. So that's what this line is. Individual routing protocol have no control over what gets installed into the IP routing table. Routing protocol has got no control. Because I'm a BGP, you have to listen. No. Routing table will say, I don't care about routing protocol. I take your recommendation if your administrative distance is lower. That's all. So EIGRP, in this example, you don't have BGP, so RAPE, OSPF, EIGRP. I didn't bring BGP in picture because BGP has got two administrative distance, 220 and 200. So I don't want to confuse. Anyway, if you have IBGP, then IBGP would have come here. Sorry, if you have EBGP, which is only 20, it would have come here, not IBGP. IBGP is 200. So now routing table has got the route from one of the source whose administrative distance is lower. Again, if there is multiple paths, it is not guaranteed that it will go via the second path or the first path. It all determined by the switching process. Alright, that's all the new story which I added for you in this presentation, BGP presentation. Now let's go back to the BGP topic. See, this is the order in which the attributes are going to be evaluated. The route selection decision process will be based on this. First, it will check whether the next hop given by BGP is a reachable next hop. Whether it is a valid next hop. Here. Whether it's a valid next hop. You say we got two paths. This router is giving an update for a destination. Let's say the destination is alpha. Router C is also giving a route for alpha, like router B was giving. RC also gives the route for alpha to RA. Now router A will check whether I'm able to reach the next hop given by these two routers. Say for example, router B has given a next hop which is pingable from here but not pingable from RA. RC given next hop is not pingable. RB given next hop is pingable. Then what happens? RA will decide to take this path as the best path. And that path only BGP will recommend to the routing table in router A. So there is no need for checking any of this attribute. Why? Because already there is a tie break. One next hop was not reachable. You got multiple paths, but one was not reachable, the other one was reachable. The one which is not reachable is eliminated. So there is no need for checking any of this attribute. Listen, how important is this to troubleshoot, in BGP. Let me speak something in offline. Only when we know how this BGP route selection decision process works, you will be able to troubleshoot BGP. When someone says, this is what I expect as a path selection, when someone says this is what the path needs to be, you need to have the knowledge of what I just covered in these pages, plus you also need to know how BGP decides the best path. BGP is route selection decision. When you have this both knowledge, you will be the hero of BGP. Otherwise, you will be considered as zero only if you don't know this proper and these things which we spoke this morning. Simply enabling some command is not heroism. It's only comedian. So, you see, if we don't know these things, we will not be able to figure out the problem. When the next hop is unreachable, whatever the troubleshooting you do, it's waste. Packet cannot go that path. You may go and configure AS path, you may go and change the attribute local preference. What is the use? No use. I know how to change the local preference. I know attributes, but I don't know the fundamental. When I don't know the fundamental, whatever the local preference you configure, it's not going to be effective there. Why? Before getting into the very first attribute, what it checks whether the next hop is reachable. BGP decides whether to go this way or this way R1 is receiving routes for alpha network, some destination alpha. First thing it sees, do I have the reachable next hop via router A and router B? If router B is given next hop is unreachable, then it eliminates, finish. It will go via router A. There is no need for now to check any of this attribute. So if you have set attribute thinking that I have set this attribute for path via router B, it won't be useful. Because path B, in the very first constraint, it has failed. Right? So, valid next hop is the very first attribute, I'll say. You can also call it a zeroth attribute. Because the first attribute is wait. Fine. Now, about the wait we already spoke. This is local to the router. The default wait is 0. The highest is preferred. The default is 0, highest is preferred. When you want to decide a path based on the wait, the impact will be only on that router, not for the entire autonomous system. So if one router you want to go via this way, not this way, then you may go and set wait on this router towards this direction. But if you wish to select one direction, you got two exit. You got many routers. You want every router in this autonomous system to exit this way, not this way. Then you go and set high local preference on this router. The default local preference is 100. You set high local preference. All the router, including this router, it will go only via this way. So if you want the impact to be only on one router, you set wait. If you don't set wait, the default wait is 0, then there is a tie. Listen. Only when there is a tie in wait. Only when there is a tie in wait, it will check the local preference. So we need to check these things. When I configure local preference for a path selection, I need to make sure the wait is not set. If wait is set, the tiebreaker is wait. Wait says on this router, go this way. Don't go this way. Go this way. Now if you set local preference in this router saying 200, this router will go, all this router will go, but this router will still go via this way because the wait is set this direction. All other router will go via 200, whereas this router will not consider local preference, because before local preference comes what? Wait. On this router you have set wait to go via the upper path. So that router alone will go via upper path. In case if you don't configure wait, if you have not configured wait, then even that router will come via the below path. Even this will now come via this path. So local preference is a tiebreaker when we set local preference. The default is 100. Only when you set local preference it will become a tiebreaker. What if I don't have local preference? No wait. No wait, no local preference. Then it prefers the route originating by the local router. If the same destination is locally originated, directly connected, it will have next stop as 0. That will be preferred. See, these things will be more clear when I do and show. Next, if none of the next stop is 0, 0, 0, then there is a tie. It comes to shortest AS path. In a big network, you'll see most of the, not most, at least half of the path selection is based on the shortest AS path. You know what is shortest AS path. I think I don't need to explain that. You have less number of hops, AS hops. One path is showing like you have 5 autonomous system in between. The other path is showing you have 6 autonomous system in between. Only when there is tie in this above, it is going to select via this direction, because the hop is less, shortest AS path. Next, if there is tie in this also, it prefers the lowest origin code. See, lowest. I is lower than E. E is lower than question mark. I have also said repeatedly in your classes that there is no more E. I means network introduced using network command. Incomplete question mark means introduced via redistribution. So let's say if K is providing I for a destination, for the same destination L is providing question mark, your autonomous system will decide to go via K because K is smaller. K has got I, which is smaller than question mark, lowest origin code. Provided the above should be a tie, repeating again. First 4 should be tie for the path to be as per this. First 4 should be tie. Only then, based on fifth attribute, BGP can recommend, not guarantee, BGP can recommend this path to the routing table manager. See, on top of BGP, that one which we learned this morning is more important. BGP is going to recommend based on this attribute configuration. Again, there is a evaluation done by routing table manager. Now, if there is tie in this, it prefers the lowest MED. MED is nothing but multi-exit discriminator. If you have two connections to the same autonomous system, you need this. And we spoke much about this in our classes. Our neighbor autonomous system advertises with MED, and our router will prefer the neighbor autonomous system, so ingress router whose MED is lower. But what if I don't have dual homing? Then there's no use of looking at this. It won't look into this. It will come here. It prefers the eBGP path over IBGP. So if one of your neighbor is eBGP, the other one is IBGP, it is going to be based on this. What if both are IBGP? None of them are eBGP. Then it will see which IBGP neighbor has got the low metric to be reached. Meaning, it will check the routing table and see which IBGP neighbor has got low metric, closest. That way. So it now depends on what? The routing table manager.
Could you repeat the step 8?
Yeah, repeating again step 8. See, it's very easy because today we have spoken a lot about routing table. So this point, if you understand now, you understood. Otherwise, you will never understand. So better understand now. You see, for router 1, you can go via router 2, you can go via router 3. See, this point prefers the eBGP path over IBGP, but for R1 there is no eBGP. Both are IBGP. Now, because there is a tie in this, it comes to 8. Now router 1 will see the routing table for determining whether to go via R2 or R3. It will check the routing table. Routing table says the metric to reach R2 is 10, the metric to reach R3 is 15. So now what R1 does? It says, let me go via R2, closest neighbor. Is it not an IGP neighbor? IGP means what? Inside the autonomous system. He's the closest IGP neighbor. So R1 decides to go via this way, eliminating this path. What if both are same IGP metric? Both are same. There is no close or far. Then it comes to ninth one. Prefers the oldest route for eBGP path. Meaning, R1 will see who gave me the route first. R2 gave me the route to reach alpha, or R3 gave me the route to reach alpha. Who gave me first? Whose one is the oldest one? That one it will prefer. Let's assume there's a tie in that, meaning both came at the same milli-microsecond and gave me the route. Very rare case. In that scenario, it see whose router ID is lowest. See, router 2 has got a router ID. Router 3 also has got a router ID. Whose is lower? It prefers that one. So this will be a tiebreaker. Very rare chance that two neighbors having the same router ID. Very rare, very rare. In that situation, in eBGP there are some chances like that. In that situation, it prefers the neighbor whose IP address is lower. It prefers the neighbor whose IP address is small. Definitely a IP address, whether it is in the WAN or a LAN, it will be different, unique for every device. It will be unique for every device. So every device will have different IP address. So it prefers the path with the lowest neighbor IP address. This one you should know in sequence by heart. You need to know these things, you know. If you close the eye, you should be able to say this thing in order. Valid next hop. Highest weight. The default is 0. Weight is local to the route. Highest local preference if there is tie in weight. Default is 100. Higher is preferred. It is for the entire autonomous system. Local origin router. AS path. Origin code. MED. eBGP is preferred over eBGP. The closest IGP path to the neighbor. The oldest router to the eBGP. BGP's router ID should be lower. IP address should be lower. That's all. Just by closing, see. My initial day of BGP learning, I did this. I never forgot this sequence. That helps you to troubleshoot when BGP is in your network. Very fast troubleshooting. Otherwise, to come to a conclusion about a trouble will be taking long time. Sometime you will not find a solution. I want to talk something in offline.